Okay, hi everyone. So today we have task to solve problem solving, which is title is crystal binding. So my name is NURUL FITRAH BINTI RAMANI. My matrix number is 203183. And my group members is NURUL NATASHA, AFIQAH BINTI AKASHAH, SITI NUR AMIRA, Nur SHAHADAH, myself, NURUL ALYAA AZIRA, INSYIRAH BINTI ABDULLAH, and AZIMAH BINTI AZMI. So the question stated to assume the energy of two particles in the field of each other is given by the function UR is equal to negative A divided by R plus B divided by R to the power of A, where A and B are constant and R is the distance between the centers of the particle. So today we would like to discuss and try to solve the problems together. Then I will pass next presentation to INSYIRAH.
So I will present this graph. This graph shown on the slideshow considers the interaction between two isolated atoms as they are brought into close proximity from an infinite separation. This graph also shows the energy particle system changes as a function of internuclear changes. It is convenient to work with energy than force. So for the first graph, we will talk about the energy. The distance between the net energy between the R naught is actually the bonding energy, R naught. The distance of R0 to the intersection of net energy is the interaction energy or potential energy between two isolated atoms at separation R. It is related to the force by some equation, and the total energy has a minimum at the point of equilibrium separation. The bonding energy, which is E naught, corresponds to the energy at R negative. So at the largest distances, the energy is 0, meaning that there is no interaction between the atoms. So the atoms are not bonded to each other. And the distance where the energy is minimum occurs when the net energy is at the equilibrium bond length. The x-axis on the graph shows the radius of atom to denote the distance between the two particles. Note that the net energy does not move to 0 because as it moves to infinity of interatomic separation R, the energy of the atom will become negligible. At the infinite distance of R, it's not 0, but it's negligible. So the graph of attractive force is going down to ultimately infinity as we get closer approximate to 0. So the repulsive energy of the particles are getting lower as the radius increase closer to infinity, and the attractive energy is getting higher as it goes further. And for the second graph, can be shown that the radius gets separated from the atom. As the radius gets separated from the atom, the repulsive force gets closer to 0, while the attractive force is 0. This is due to the particle energy of force becoming equilibrium. The R naught for the second graph is also the same with the first graph, which is the bonding energy between the two atoms. That's it for the graph.
Okay, from what INSYIRAH explained just now, we will try to solve this question. This is A, to show that if the particles are pulled apart and the molecules will break as soon as R is equal to 36 times B divided by A to the power of 1 over 7 is equal to R naught multiplied by 4.5 to the power of 1 over 7. So the solution is, based on what INSYIRAH said just now, the equilibrium point is du over dr is equal to 0. So we have potential u times r is equal to negative a divided by r plus b divided by r to the power of 8. Then when we relate to equilibrium point, which is du over dr is equal to 0, we just substitute into the equation, which is a is equal to r naught to the power of 2 minus 8b divided by r naught to the power of 9 is equal to 0. And then we try to find r naught to the power of 7 is equal to 8b divided by a. Then we find r naught, which is it will be equal to 8b divided by a to the power of 1 over 7. Then from that, we can relate to the force and the particle and how the particle will break. So I will pass the next presentation to AZIEMAH.
All right, so for the force between two particles, we use the formula Fr equal to negative du over dr, which means we have to differentiate the original equation u, which is given in the question. The original equation, which is u equal to a over r, negative a over r minus a minus b over r to the power of 8. So when we differentiate the equation, we will get the original differentiation. We will get a over r naught to the power of 2 minus 8b over r to the power of 9. But we have to put the negative because the force between two particles is negative. When we put the negative, we will get the final equation, which is negative a over r naught to the power of 2 plus 8b over r naught to the power of 9. And then the next presenter will Natasha will explain the particle where the particle will break.
Okay, so thank you, Jima. So after we get the equation number 2, equation number 3, the particle will be break when df over dr equal to 0, or we get 2a over r power of 3 minus 72b over r power of 10 equal to 0. So after we substitute and put the value, we will get the equation number 4, which is r equal to 36b over a power of 1 over 7. So using the value of equation 2, we will get the final r equal to 36 power of 1 over 7 times r naught over 8 power of 1 over 7. So I will pass to the next presenter for the next question.
Thank you, Natasha and AZIEMAH. But I think this answer is related to the concept of repulsive and attractive. Is there someone willing to define or to share any info about repulsive or attractive concept?
Okay, so basically the repulsive and the attractive force concept is related to intermolecular forces. So what is intermolecular forces? So intermolecular forces is actually force of attraction or repulsion which acts between neighboring particles. So as for the attractive force, it dominates to the distance at which two molecules comes into contact, and then the strong repulsive forces come into play and the potential energy of two molecules rises rapidly. So example of attractive forces would be dipole-dipole bond, van der Waals, and then ionic and hydrogen bond. Yeah, and after that, we should also understand what is repulsive force. So repulsive force is the repulsive part of the intermolecular potential, where it is essentially a manifestation of the overlap of the wave function of two species in conjunction with the Pauli exclusion principle. So it reflects the possibility for electrons with the same spin to occupy the same region of space. So that's all for me. Moving on to the next question.
So for question B, the question asks, in stable configuration, the energy of attraction is 8 times the energy of repulsion. So we look on the first equation that provided, which is U R equal to negative A over R plus B over R to the power of 8. This question asks for the stable configuration of the energy of attraction. So the stable, it means that the energy of attraction equal to the energy of repulsion. So A to the power A over R naught equal to B over R over 8. And then we simplify the equation. We get like this, A over B times R to the power of 7. R to the power of 7 we can see as equation 2 from the equation A. Then we simplify it into the equation, which is A over B times 8 B over A. Then we just cancel A over B times B over A as it equals to 1. Then it will become 8. So I'll pass the presentation to AMIRA.
Okay. Okay, so part C, the question is also show that the minimum force required to break the molecule is equal to A power of 9 over 7 over 36B power of 2 over 7 multiplied by 1 minus 8 over 36. So for this part, we use the equation 3 and 4 in part A to solve this question. So since the question state that the minimum force, so we have considered F0 is equal to negative. So that's why we put negative in the equation. So the first one is minimum force, which is F is equal to negative A over R square plus 8B over R to the power of 9. Okay, so that is the equation from part A. And then next we substitute equation 4, which is R is equal to 36B over A power to the 1/7 into the equation 3. And then we have calculate it. So at last we can show that the minimum force is required to break the molecule is equal to negative A to the power of 9/2 over 36B to power 2/7 multiply with 1 minus 8/36. That's all.
Okay, so that's all from us. Thank you.